Hello, my friend. If you have trouble falling asleep, then you are in exactly the right place. Tonight, we are stepping into one of the deepest questions science has ever asked. Not just how the universe began, but whether the beginning was really the beginning at all. Few ideas are more fundamental than this, because hidden inside that question may be the story of time itself, and whether time had a past we can barely imagine. Somewhere in this journey is a possibility so unsettling and so elegant that it can change the way you think about existence forever. Let your mind settle as we move slowly through strange and beautiful possibilities, guided by science and by wonder. So get comfortable, breathe a little deeper, and let us begin. Chapter 1. The problem with the word before. Few questions feel more thrilling or more fundamental than this one. If the universe had a beginning, what, if anything, came before it? At first, the question sounds perfectly ordinary. In daily life, everything seems to have a before. Before sunrise, there is night. Before a seed becomes a tree, there is a smaller seed, and before that a flower, and before that another tree. Our minds are built around sequence. We understand the world by placing events in order. One thing happens, then another thing happens after it. So when we hear that the universe began in the Big Bang, it feels natural to ask what happened earlier. But the early universe is one of the rare places where common sense begins to fail us. The problem is not that the question is silly. The problem is that the word before may not mean what we think it means when we carry it all the way back to the beginning of cosmic history. In everyday speech, before assumes that time is already there, like a road stretching into the distance. Yet modern cosmology suggests that time is not a stage outside the universe on which the universe appeared. Time, at least as physics describes it, is tied to the universe itself. If that is true, then asking what happened before the beginning may be less like asking what happened before sunrise and more like asking what lies north of the North Pole. To understand why, we have to clear away one of the most common misunderstandings about the Big Bang. Many people picture it as an explosion that happened somewhere inside a dark, empty void. In that picture, there would be a location where the blast occurred, surrounding empty space into which debris flew, and a clock outside it all measuring the scene from a safe distance. That image is dramatic, but it is not what the standard cosmological model describes. The Big Bang was not an explosion of matter into pre-existing emptiness. It was the early expansion of space itself. There was no ordinary outside waiting around the edges for the universe to grow into, at least not in the standard picture. The galaxies are not flying away from one central point through a larger room. Rather, the distance between regions of space changes over time because space itself evolves. This is one of the greatest changes that came with Einstein's picture of the cosmos. In older ways of thinking, space and time were often treated as fixed containers. Matter and light moved around inside them, but the stage itself remained untouched. In modern relativity, space and time are woven together into space-time, and that space-time is dynamic. It can stretch, curve, and respond to energy and matter. Gravity is deeply related to the geometry of space-time itself. That means the history of the universe is not just a history of things changing within time. It is also a history of time and space taking the form they do. When that backward extrapolation is pushed far enough using the equations of general relativity, something remarkable happens. Distances shrink, Densities rise, temperatures rise, and the mathematics points toward an extreme state in which our ordinary description breaks down. This limit is often called the initial singularity. It is tempting to imagine the singularity as a tiny physical object, like a dot of compressed matter. But in careful scientific use, a singularity is better understood as a sign that the theory has reached a boundary where it no longer gives a complete physical description. It marks a breakdown in the structure of space-time as described by the theory. In that sense, the singularity is not a well-understood thing that physics has fully explained. It is a warning sign that we have driven our current framework into a regime where it cannot be trusted without something deeper replacing it. That point is crucial because it means science does not simply say, with full confidence, that there was a neat instant called the beginning and nothing at all on the other side of it. What science says more carefully is that our present successful theory of gravity, when pushed back far enough, runs into a limit. Near that limit, quantum effects are expected to become important, and general relativity alone is not enough. In other words, the question of what came before the Big Bang is not ruled out by science, but neither is it answered by the standard cosmological model on its own. There is another layer to the problem, and it concerns the meaning of time itself. In ordinary life, time feels like the most obvious thing in the world. It flows. It carries us from memory into expectation. But physics forces us to be more careful. Time in science is not defined by feeling. It is tied to change, order, measurable intervals, and the structure of physical law. If the very early universe was a regime in which our ordinary space-time description dissolved, then our everyday sense of time may not apply there in any straightforward way. The language of earlier and later may be useful only after the universe reached a state where space-time behaved classically enough for clocks, distances, and causal order to make familiar sense. This is why some cosmologists and philosophers of physics say the question may be ill-posed in its simplest form. That does not mean it is meaningless in every possible theory. It means that within the usual framework, the word before may fail to refer to anything physical. The useful analogy is asking what is to the left of the leftmost edge on a map when the map itself ends there. Sometimes there really is more land beyond the border and the map is incomplete. But sometimes the edge is not a border within the territory. It is the edge of the territory as represented by that system. The challenge of early universe physics is to figure out which sort of case we are dealing with. There is an important reason scientists do not simply stop there and declare the matter closed. The history of physics teaches caution whenever a successful theory breaks down under extreme conditions. Newton's theory worked beautifully for many purposes, yet later had to be absorbed into a deeper framework. Classical physics described much of the visible world, yet failed at the smallest scales where quantum theory became necessary. In the same spirit, many physicists suspect that the apparent beginning described by classical cosmology is not the final word. A future theory of quantum gravity may reveal that the universe emerged from an earlier phase, bounced out of a contraction, tunneled from a quantum state, or followed some path that makes our current categories look incomplete. At the same time, it is important to stay disciplined. The phrase "before the Big Bang" can easily invite pure imagination. It can tempt us to smuggle in images of empty darkness, hidden dimensions, previous lives of the cosmos, or a clock ticking in some greater background. Some of those possibilities may appear in speculative models, but none should be accepted merely because it sounds vivid. In science, a hypothesis earns respect not by being dramatic, but by being mathematically coherent, physically motivated, and at least in principle, connected to evidence. One more detail matters here. When people say science has seen back to the Big Bang, that is not literally true. The oldest light we can observe directly comes from a later time, when the universe had cooled enough for light to travel freely through space. From there, physicists infer still earlier stages using theory and other evidence. That means our picture of the earliest history is powerful, but it is not a direct photograph of the first moment. The closer we move toward the beginning, the more we rely on models, and the more carefully those models must be tested. So the first task of this video is not to answer the question too quickly. It is to refine it. When we ask what came before the Big Bang, we are really asking whether the beginning of our observable cosmic history was an absolute beginning of time, a boundary of an incomplete theory, or a transition from some earlier state that current physics only partly glimpses. Those are very different possibilities. Each leads to a different picture of reality, and each demands a different way of thinking about time, causation, and existence itself. That instability is not a failure of science. It is one of the reasons this subject is so beautiful. The closer we get to the deepest layers of reality, the more carefully language must be used. Words that seem simple in ordinary life can become delicate instruments at the edge of knowledge. Before is one of those words. It works wonderfully for breakfast, memory, and history. But near the beginning of the universe, it may need to be rebuilt from the ground up. And perhaps there is something quietly comforting in that. The universe does not owe us answers in the shape of our everyday intuitions. It only invites patience. As the day loosens its grip and your thoughts begin to slow, you do not need to solve the beginning tonight. It is enough to rest in the wonder of the question and to let the vastness of it grow gentle around you. Chapter 2. Where the standard Big Bang model reaches its limit. The standard Big Bang model is one of the great achievements of modern science, not because it claims to explain everything, but because it explains so much of the universe with remarkable success before it finally reaches a wall. When people hear the phrase Big Bang, they often imagine a single dramatic instant that explains all of reality at once. But in practice, the standard model of cosmology is not a complete story of absolute origins. It is better understood as a very successful description of the universe once it was already in an extremely hot, dense, rapidly expanding state. From there, it traces how the cosmos cooled, how simple particles formed stable matter, how light eventually began to travel freely, and how galaxies later grew from tiny early irregularities. It gives a history of evolution. What it does not fully give is a final explanation of the deepest starting point itself. That distinction matters. A scientific model is judged by what it can predict and explain within its range of validity. In that sense, the standard Big Bang picture is extraordinarily strong. It explains why distant galaxies, on average, are observed to be moving away from one another. It explains why the universe is filled with a faint thermal glow left over from a much hotter early stage. It explains why the cosmos contains large amounts of hydrogen and helium, along with only small traces of certain other light elements. It also explains how slight differences in density in the early universe could later grow into stars, galaxies, and the large-scale cosmic web. These are not vague impressions. They are deep successes tied together by one basic idea. The universe has been expanding and cooling from a much hotter and denser condition. You can think of this model almost like running a film backward. Today, the universe is large, cold by early universe standards, and full of structure. If space expands over time, then in the past, everything was closer together. Matter and radiation were packed more tightly. Temperatures were higher. The farther back one goes, the more extreme the conditions become. This backward reasoning is not just imagination. It is built into the mathematical framework that connects the geometry of the universe to its contents. As the model is carried backward, it passes through several stages that are on especially firm ground. One of the most important comes when the universe was still hot enough that matter existed not as atoms, but as a glowing plasma of charged particles and light. In that state, light could not move freely for long because it constantly scattered from free electrons. The universe was, in effect, opaque. Later, as the expansion continued and the temperature dropped enough, electrons could settle into stable atomic structures with nuclei. At that point, light no longer scattered so easily and began streaming across space. The relic of that transition still fills the cosmos today as the oldest light we can directly observe. It is one of the strongest pillars of the standard picture. Another major success comes even earlier, when the universe was hot and dense enough for the first atomic nuclei to form. In a brief early period, simple nuclear reactions produced large amounts of helium, along with hydrogen and tiny amounts of a few other light nuclei. The predicted pattern is not arbitrary. It depends on the temperature, density, expansion rate, and particle content of the early universe. When astronomers measure the broad primordial abundances, the overall agreement with the hot early universe picture is one of the reasons cosmologists take it so seriously. This does not mean every detail is perfectly settled, but it does mean the model passes a demanding test from very early times. There is also a subtler triumph. The early universe was not perfectly smooth. It contained very small variations in density and temperature. Those tiny differences mattered enormously. Over immense spans of time, gravity amplified them. Slightly denser regions pulled in more matter and became denser still, eventually helping to build the large cosmic structures we see today. The standard cosmological framework successfully connects those early fluctuations with the later universe of clusters, galaxies, and voids. In other words, the model does not merely say the universe expanded. It also says how complexity emerged within that expanding universe. So if the model works so well, where does the limit appear? The trouble comes when we keep pushing backward toward earlier and earlier conditions. The temperatures rise, the densities rise, curvature becomes more extreme. Eventually, we approach a domain where the equations of general relativity, used in their classical form, drive the description toward a singular limit. This is often spoken of as the moment of the Big Bang itself. But that phrase can be misleading. In the strictest scientific sense, the singularity is not a fully understood physical event that has been successfully described. It is the place where the model stops being trustworthy. This is one of the most important lessons in cosmology. A successful theory can describe reality very well across a wide range without being valid under all conditions. Classical general relativity treats spacetime as a smooth geometric structure. Quantum physics, by contrast, governs the behavior of matter and radiation at the smallest scales and under extreme conditions. For most of cosmic history, the smooth geometric picture is excellent. But as we move toward the earliest conceivable stage, we expect gravity and quantum effects to become equally important. At that point, a purely classical description of space-time is no longer enough. That is why cosmologists say the standard Big Bang model reaches its limit near the earliest phase, rather than providing a full description of the ultimate beginning. It can tell us a great deal about the hot early universe after that limit, but it does not yet supply a complete, tested account of what happens when space-time itself enters a quantum regime. The true boundary is not simply that the universe becomes hot. The boundary is that our current frameworks cease to fit together cleanly under such extreme conditions. This can be hard to picture, because in ordinary life we are used to explanations continuing smoothly. If we ask what happened earlier in a familiar event, we usually expect an earlier cause in the same general language. But the beginning of the universe may not allow that kind of steady backward continuation. It may be more like following a map toward a coastline and then discovering that the paper itself ends at the shore. The question then becomes whether the land truly ends there, or whether our map is incomplete. The standard Big Bang model is powerful enough to bring us astonishingly close to that coastline. It is not, by itself, the boat that can carry us beyond it. There is another important limit built into observation itself. The oldest light we can directly receive does not come from the earliest instant. It comes from the time when the universe became transparent. Earlier than that, the cosmos was opaque to light. So even though we can infer many features of earlier stages, we do not possess a simple photograph of the first moment. Our knowledge becomes more indirect as we move backward. We combine theory, observation, and consistency checks, but direct access becomes harder. This does not make the science weak. It simply means the earliest universe must be reconstructed from traces rather than watched directly. That is also why precision matters so much. If a model is to describe the earliest stages, it must not only be mathematically elegant. It must also leave consequences that connect, however indirectly, to the observable universe. Science cannot rest on imagination alone. A proposal about the beginning becomes scientifically meaningful when it helps explain why the universe we see has the properties it has. This is where many ideas about the earliest cosmos are tested, challenged, and often rejected. Even within its limits, the standard Big Bang model teaches something profound. It shows that the universe has a thermal history. There was a time when matter and radiation behaved very differently from the way they do now. Space was not static. Structure was not always present. The calm, cold, patterned universe around us emerged from a state far hotter, smoother, and more compressed. In that sense, the model is not a failure that breaks at the beginning. It is a success so powerful that it carries us right up to the edge of a deeper question. And that deeper question is exactly where the next chapters begin. Once we understand that the standard model is reliable for a great deal of early cosmic history, but not all the way to an ultimate origin, a new possibility opens. Perhaps the hot Big Bang was not the absolute first event. Perhaps it was a transition. Perhaps it was the aftermath of inflation, a bounce from a prior contraction, a quantum emergence, or something stranger still. Those ideas are not part of the standard model itself. but they arise precisely because the standard model leaves a gap at the deepest edge. It is worth pausing here because there is something healthy in the way science reaches this boundary. Good science does not pretend to know more than it does. It does not hide uncertainty behind confidence. The standard Big Bang model has earned enormous trust because it succeeds where it should succeed, and because physicists are equally clear about where it stops. That honesty is not a weakness. It is the reason the subject remains alive. So Chapter 2 leaves us in a very particular place. We are not standing in confusion. We are standing at a frontier. Behind us lies one of the most successful reconstructions in all of science. The cooling universe, the first nuclei, the release of the oldest light, the growth of structure. Ahead of us lies the region where the known description runs thin, where gravity and quantum theory must somehow meet, and where the question of what came before the Big Bang becomes a serious scientific question rather than a casual phrase. And for now, that is enough. You do not need to force the universe to yield its first secret all at once. You can simply rest at the edge of what is known, where certainty fades gently into wonder. Let the question stay open for a little while longer, and let your mind grow quiet inside its vastness. Chapter 3. Inflation. The hidden era before the hot Big Bang. Inflation is one of the most powerful ideas in modern cosmology because it suggests that what we call the Big Bang may not have been the absolute beginning, but the aftermath of an even earlier event that reshaped the young universe with astonishing speed. By the time the standard hot Big Bang story begins, the universe is already filled with intense heat, radiation, and particles. Space is expanding, matter is interacting, and the long cooling history that eventually leads to stars, galaxies, planets, and us is already underway. Inflation enters the picture just before that familiar early phase. It is the proposal that, in an extremely early moment, the universe passed through a brief period of accelerated expansion, during which space grew at a tremendous rate. When that phase ended, its energy was transferred into hot matter and radiation, setting up the dense, glowing state that the standard Big Bang model describes so well. That distinction is essential. Inflation is not simply another name for the Big Bang. In the way many cosmologists now use the terms, inflation comes before the hot Big Bang. The hot Big Bang is the aftermath, the hot beginning of the universe as we can track it using ordinary particles, radiation, and the relics they left behind. Inflation is the proposed hidden prelude. Why was such an idea introduced at all? The older hot Big Bang picture, successful though it was, left behind deep puzzles about the large-scale structure of the cosmos. One of the most famous concerns involves uniformity. When astronomers map the oldest light in the sky, they find that the universe is astonishingly similar in temperature in regions that are now separated by enormous distances. Under a simple non-inflationary history, many of those distant regions do not seem to have had enough time to influence one another before that light was released. Yet they look strikingly alike. Inflation offers a neat way to make sense of that. It says that those regions were once much closer together, close enough to share physical conditions before they were driven far apart by rapid expansion. In that picture, the early universe had time to smooth itself on small scales before inflation stretched those once nearby patches across the sky. What looks mysterious in the later universe becomes natural if the observable cosmos grew out of a much smaller, more connected region. A second puzzle concerns the geometry of space. Observations show that on the largest scales we can measure, the universe is very close to geometrically flat. Without inflation, that near flatness appears surprisingly delicate. In a universe that expands in the ordinary way, any initial departure from flatness tends to become more important over time unless conditions were set with extraordinary precision at the beginning. Inflation changes that behavior. A period of accelerated expansion drives the observable region toward flatness in much the same way that the surface of a very large sphere can look almost flat to someone standing on it. At the heart of the idea lies a peculiar kind of energy. Ordinary matter thins out as space expands. Radiation thins out even faster. But a nearly vacuum-like form of energy behaves differently. Its energy density can remain roughly steady even while space grows. If such a component dominates the young universe, it produces a kind of gravitational effect that drives accelerated expansion. The exact microphysical origin of that energy is still unknown. In many inflationary models, it is described using a field spread throughout space, often called the inflaton field. Physicists do not yet know whether such a field truly existed or what its deeper connection to fundamental particle physics might be. Importantly, this does not mean that material objects were racing through space faster than light in the ordinary sense. Relativity forbids local motion through space faster than light, but it does not forbid space itself from expanding so that the distance between faraway regions grows faster than light. Inflation uses that distinction. It is not a violation of relativity. It is a consequence of how relativity allows space-time itself to evolve. The word brief can be misleading here. In everyday life, a brief event feels small, but in inflationary cosmology, a very brief event can have immense consequences. Even a tiny span of accelerated expansion can enlarge a microscopic region into one vast enough to contain everything we now observe. But inflation does more than smooth and flatten the universe. One of its most beautiful features is that it provides a plausible origin for the small irregularities that later grow into cosmic structure. If the very early universe contained quantum fluctuations, tiny, unavoidable variations associated with quantum fields, inflation could stretch those fluctuations from submicroscopic scales to astronomical scales. After inflation ends, those stretched variations remain as slight differences in density from place to place. Over time, gravity amplifies them. Regions that begin just a little denser than average pull in more matter, and the later architecture of the universe slowly emerges from those faint initial wrinkles. This idea connects the largest structures in existence to the smallest known features of physics. Galaxies and clusters may trace their ancestry back to quantum fluctuations in an inflationary era. That is one of the reasons inflation became more than a clever patch for old cosmological puzzles. It turned into a framework that links early universe dynamics to the observed pattern of the sky. The oldest light in the universe carries an imprint of those primordial irregularities. Its temperature is not perfectly uniform. It varies slightly across the sky, and those variations match, in broad outline, what many simple inflationary models predict. The primordial fluctuations appear to have been laid down in a very orderly statistical way, with no obvious preference for a special location or direction, and with only a gentle dependence on scale. That general pattern is one of inflation's greatest successes. This is why many cosmologists treat inflation not as a wild speculation, but as a serious explanatory framework. It helps explain why the observable universe is so uniform on large scales, why space appears nearly flat, and why the initial seeds of cosmic structure have the properties they do. At the same time, science requires honesty about what inflation has and has not achieved. There is not one single inflationary model accepted by all physicists. There is a whole family of possible versions, with different fields, different energy landscapes, different endings, and different implications. Some models fit current observations better than others. Some have been strongly disfavored. None has been confirmed in a final, unique way. We therefore have evidence consistent with inflation, but not yet a complete proof of the detailed mechanism. The distinction matters. A framework can be strongly supported without every internal piece being settled. In the case of inflation, the broad idea of an early accelerated expansion remains compatible with high-precision observations of the early universe. But the identity of the field, the exact manner in which inflation began, and the precise way it ended are still open questions. The ending matters because inflation cannot last forever if it is to lead to the universe we know. At some stage, the inflationary phase must come to a close. The vacuum-like energy driving the rapid expansion must be converted into ordinary particles and radiation. This transition is called reheating. During it, the energy of the field that drove inflation is released into the contents of the universe. Only after that does the standard hot Big Bang history truly begin in the usual sense. This is the key reason inflation belongs in a video about what might have come before the Big Bang. If inflation occurred, then the hot, dense universe of the standard model was not the first chapter. The state we often call the Big Bang would then be the result of inflation ending, not the absolute first moment of all existence. In that picture, our familiar early universe is born from a transformation. Of course, this does not solve every mystery. Inflation itself may still have had a beginning. Perhaps it emerged from a quantum event. Perhaps it was part of a larger process. Perhaps it arose after a bounce from a previous phase. Inflation answers some questions magnificently, but it also opens new ones. Today, the observational situation is both encouraging and incomplete. Measurements of the oldest light strongly support the general kind of primordial fluctuation pattern that many simple inflationary models produce. Observations also continue to show that the universe is very nearly flat on large scales. At the same time, one of the most anticipated signs of inflation, a confirmed detection of primordial gravitational waves imprinted in the polarization of the oldest light, has not yet arrived. That absence does not rule inflation out. It narrows the range of viable models and keeps the story unfinished. So inflation stands in an intriguing place. It is not mere fantasy, because it was proposed to solve concrete problems, and because many of its broad expectations fit the observed universe surprisingly well. But it is not complete certainty either, because the underlying mechanism remains unknown, and the decisive clues that could uniquely pin it down are still being pursued. It is a bridge theory stretching from the familiar hot early universe toward a deeper and more hidden past. And that is what makes it so important in this story. Inflation invites us to loosen our grip on the idea that the Big Bang was simply the first instant of everything. It suggests that the hot beginning we can describe may have been preceded by a quieter, stranger, more powerful phase that prepared the universe before filling it with light. For now, that possibility is enough to hold gently in the mind. You do not need to resolve every open question before sleep. You can simply picture the young universe widening in silence, smoothing itself, planting the faint seeds of every future star, and then giving way to warmth and light. Let that hidden era recede softly into the dark, and let the day recede with it. Chapter 4. Quantum Beginnings. Did the universe tunnel into existence? One of the strangest and most daring ideas in cosmology is that the universe may not have begun as a classical event at all, but as a quantum one. By the time we speak about ordinary cosmic history, we are already describing a universe with space, time, expansion, temperature, and matter. But if we keep asking what lies deeper than that, physics begins to change its language. At very early stages, the smooth picture of space-time given by classical gravity is expected to stop being complete. The universe may then need to be described in quantum terms. That shift is not a small adjustment. It changes not only what kinds of events are possible, but also what it means to ask how the universe began. Quantum theory is famous for allowing processes that have no close parallel in everyday life. One of the best known is tunneling. In ordinary experience, if a ball does not have enough energy to roll over a hill, it stays on one side. In quantum physics, things are less rigid. A particle can sometimes be found on the far side of a barrier, even when classical reasoning would forbid it. This is not because the barrier disappears. It is because quantum systems are described by probabilities and amplitudes rather than by a single, sharply defined path. The provocative question is whether something like that could apply to the universe as a whole. Could the universe have originated through a quantum transition, in which a state with no classical space-time gave way to a small expanding universe? This is the basic intuition behind tunneling proposals in quantum cosmology. The popular wording often says that the universe tunneled from nothing, but that phrase needs to be handled very carefully, because the word nothing can easily mislead. In ordinary speech, nothing means absolute non-existence. In these models, it usually means something much narrower and much more technical. It does not mean an empty room waiting around before creation. It does not mean a dark vacuum inside a larger space. And it does not mean that physics has solved the philosophical question of why there is something rather than nothing. Instead, it refers to the absence of a classical space-time background. The proposal is that the universe may not have emerged from pre-existing space and time, but from a quantum condition in which our usual classical description of space and time does not yet apply. This is one reason the subject is so difficult to explain. In ordinary quantum mechanics, there is usually already a stage on which events unfold. There is a laboratory, a clock, a background time parameter, and some quantum system being studied. In quantum cosmology, the universe is the system. There is no external laboratory. There is no outside clock standing apart from the cosmos and measuring its birth from a safe distance. That means that mathematics and interpretation become much more subtle than in familiar textbook examples. One approach is to speak of a wave function of the universe. In standard quantum theory, a wave function captures the range of possible states of a system and how those possibilities are weighted. When the same idea is applied to the universe, the wave function is not just a function of matter inside space. It also involves the geometry of space itself. In other words, the universe is treated as a quantum object whose possible states include different possible spatial configurations. This does not mean the universe is a tiny particle. It means that at the deepest level, we may need a quantum description of geometry as well as matter. From that viewpoint, the beginning of the universe may not be a sharp classical point at all. It may be more like a transition from a quantum regime to a classical one. In that transition, a small universe with a definite expanding history can emerge from a state that cannot be described using ordinary classical pictures. Once that happens, space-time becomes well-defined enough for concepts like duration, distance, and causal order to make sense in the familiar way. The beginning, then, is not necessarily the start of time inside a bigger time. It may be the emergence of classical time from a deeper quantum condition. The tunneling proposal associated with Alexander Vilenkin gives one especially clear version of this idea. In simplified models, the universe can be represented by a quantity related to its overall size. The mathematics then resembles the behavior of a quantum system facing a barrier. On one side is the absence of a classical universe of finite size. On the other side is a tiny but non-zero universe that can expand. Classically, the passage would not occur. Quantum mechanically, it can. The universe can be said to nucleate through a tunneling event and then begin expanding. That picture has a certain elegance because it avoids imagining a pre-existing classical world in which the universe merely appears as one object among others. It tries instead to describe the origin of the classical universe from within a quantum framework. Once the universe appears on the far side of the barrier, it can grow, and under suitable conditions, it may then enter an inflationary phase, which in turn sets up the hot, dense early state discussed in the previous chapter. So tunneling is not usually presented as the full visible universe popping into existence in its present form. It is better thought of as a hypothesized quantum birth of a very small early universe. A related but distinct line of thought is the no-boundary proposal associated with James Hartle and Stephen Hawking. This idea is not usually described in terms of tunneling from nothing in quite the same way. Instead, it suggests that the universe may be finite and self-contained without a past boundary of the ordinary kind. In rough intuitive language, the earliest stage of the universe may behave more like a rounded surface than like a sharp edge. The important point is that both the tunneling approach and the no-boundary approach belong to the same broad family of efforts. They try to replace the crude idea of an initial singularity with a quantum description of the beginning. These proposals are exciting, but they are also unfinished. Quantum cosmology sits at the meeting point of general relativity and quantum theory, and physicists still do not possess a complete and experimentally confirmed theory of quantum gravity. Many calculations in this subject rely on strong simplifications. Instead of describing every detail of a complicated universe, they work with highly idealized models in which only a few variables are allowed to change. These settings are useful and often mathematically elegant, but they are not the final theory of reality. They are clues. This is why caution matters so much whenever people say that physics has shown the universe came from nothing. Physics has not established that claim in any final philosophical sense. What it has done is develop mathematically serious proposals in which classical space-time is not fundamental all the way down, and in which the universe may originate through a quantum process, rather than through a classical beginning with a prior time coordinate. That is already a profound shift, but it is not the same as solving every question that human language can attach to the word existence. There is also the issue of testability. Quantum beginning proposals are hard to test directly because they concern the deepest and earliest regime of all. Still, they are not entirely cut off from evidence. Different proposals can favor different kinds of early universe histories. Some are more compatible with inflation than others. Some may imply different probabilities for the amount of inflation or the broad features of primordial fluctuations. In that indirect sense, observations of the early universe can constrain the space of quantum origin models, even if they do not yet deliver a simple, decisive signature. Another subtle point concerns time. In everyday thinking, a tunneling event sounds as though it must happen at some earlier moment and then be followed by later moments. But in quantum cosmology, that intuition can fail. If classical time itself emerges only after the universe becomes large and regular enough, then the tunneling language is partly metaphorical. It points toward a quantum transition, but not necessarily a transition occurring inside a pre-existing clockwork. What makes the idea especially compelling is that it does not merely add mystery for its own sake. It tries to explain why a classical expanding universe exists at all. Instead of assuming space-time and then asking what occurred within it, it asks whether space-time itself could emerge from a more fundamental quantum description. In that sense, quantum beginning models shift the problem to a deeper level. They do not simply move the starting line. They question whether the starting line was ever classical to begin with. So, did the universe tunnel into existence? At present, the honest scientific answer is that it may have, but we do not know. Tunneling proposals are mathematically serious, conceptually rich, and important in the history of quantum cosmology. They offer a possible route by which a classical expanding universe could arise without presupposing a classical earlier time, but they remain hypotheses, not confirmed facts. And perhaps that alone is enough for tonight. The universe may have begun not with a bang in the ordinary sense, but with a quiet shift from possibility into form, from a realm where familiar space and time had not yet settled into place. You do not need to picture it perfectly. You only need to let the mystery become gentle. Let the questions soften at the edges, and let your thoughts drift with them into rest. Chapter 5. The Big Bounce. Was our expansion born from an earlier collapse? The Big Bounce is one of the boldest alternatives to the idea of a cosmic beginning, because it suggests that the expansion of our universe may have emerged from an earlier phase of contraction rather than from an absolute first moment. In the standard picture of cosmology, if we follow the expansion of the universe backward, everything becomes denser, hotter, and more compressed until the classical equations point toward a singularity. As we have already seen, that singularity is usually understood not as a well-described physical object, but as a sign that the theory has been pushed beyond the regime where it can be trusted. The bounce idea takes that warning seriously. Instead of accepting the singularity as the final word, it asks whether the universe might have passed through a minimum state and then turned outward again into expansion. The basic picture is simple to state, even if it is difficult to realize in detail. Before the hot expanding phase that eventually gave rise to stars and galaxies, the universe would have been contracting. Distances between regions would have been shrinking rather than growing. Densities and temperatures would have been rising. But instead of ending in a breakdown where volume goes to zero and curvature becomes infinite, some new physical effect would intervene. That effect would halt the collapse and reverse it. The result would be a bounce, contraction giving way to expansion. This picture is attractive for a very clear reason. It tries to remove the singular beginning from the story. If the universe can pass smoothly, or at least non-singularly, from contraction into expansion, then the Big Bang is no longer the first instant of everything. It becomes the hot aftermath of a reversal. In that sense, the bounce idea belongs naturally in any discussion of what might have come before the Big Bang. It says that what came before was not emptiness, nor a separate external realm, but an earlier cosmic phase. That possibility has a certain intuitive appeal. In many areas of physics, when a theory predicts an infinite quantity, physicists suspect that the description is incomplete. The singular beginning may therefore be less like a final answer and more like a signpost toward deeper laws. A bounce provides one possible replacement. It preserves the large-scale history we can observe after the hot beginning, while changing the part of the story that lies closest to the limit of classical gravity. Yet the idea is much harder to build than it first appears. Under ordinary classical general relativity, a contracting universe filled with normal forms of matter does not generically bounce in a smooth way. Instead, the contraction tends to continue towards singular behavior. To obtain a bounce, something unusual usually has to happen. The source could be a new kind of matter, an effective negative pressure, a modification of gravity, or quantum gravitational effects that become important at extreme density. In other words, a bounce is not what the simplest classical equations automatically do. It requires additional physics. One important family of bounce models appears in loop quantum cosmology. In that framework, ideas from loop quantum gravity are applied to highly symmetric model universes. The smooth geometry of space-time is replaced, at the deepest level, by a quantum geometry with a fundamentally discrete character. When the universe becomes extremely dense, those quantum geometric effects can act in a way that prevents the classical singularity. Instead of the collapse continuing without limit, the evolution turns around. In this setting, the Big Bang is replaced by a bounce. This is one of the clearest and most developed examples of singularity resolution leading to a bounce, although it remains part of an unfinished program of quantum gravity rather than an experimentally confirmed final theory. Other bouncing models rely on different mechanisms. Some use modified theories of gravity. Some involve unusual fields whose energy conditions differ from ordinary matter. Some arrange the contraction so that special dynamics dominate near the bounce and allow a smooth transition. The details vary widely, which is one reason the phrase big bounce can be misleading if it sounds like a single theory. It is really a broad class of ideas united by one central proposal. The expanding universe was preceded by contraction, and the transition between the two did not pass through a classical singularity. A common misunderstanding is to imagine a bounce as simply running our present universe backward until everything crunches and then rebounds like a ball. In reality, the physics is subtler. The contracting phase could have had properties very different from the later expanding one. The geometry might have evolved in delicate ways. The bounce itself could have been governed by quantum effects or by modified gravitational behavior, rather than by any familiar material impact or collision. So while the word bounce sounds mechanical and almost playful, the actual proposals are mathematically sophisticated and often conceptually demanding. Another important point is that a previous contraction does not necessarily mean our own future universe must one day recollapse. Older cyclic pictures often imagined repeated expansions and contractions extending indefinitely. Some modern models do explore repeated cycles, but others only claim that our current expanding phase had one earlier contracting predecessor. In those cases, the bounce is a statement about the past, not a prediction that cosmic expansion must soon reverse. That distinction matters, especially because current observations indicate that the expansion of the universe is accelerating rather than slowing toward an imminent collapse. A major scientific question is whether a bouncing universe can explain the observed large-scale smoothness and the origin of cosmic structure as well as inflation does. Some bounce scenarios attempt to do exactly that. In matter bounce models, for example, fluctuations can be generated during contraction and carried through the bounce into the expanding phase, where they later seed galaxies and clusters. Other bouncing scenarios use a very slow, smoothing contraction before the bounce so that the universe becomes more homogeneous and well-behaved. In principle, this allows a bounce model to address some of the same observational questions that inflation was designed to answer. But here we arrive at one of the central challenges. Contraction is not automatically gentle. In many cases, as the universe contracts, anisotropies can grow. That means direction-dependent distortions in the geometry can become increasingly important. Instead of remaining smooth and nearly uniform, the universe can become chaotic and violently uneven as it approaches high density. This is one of the major obstacles in bounce cosmology. To obtain a realistic bounce that leads to a universe like ours, the model must control these instabilities and keep the contraction sufficiently smooth. Some proposals do this with special forms of matter or particular contracting phases, but it is not a generic outcome. There are also challenges involving perturbations, which are the tiny initial irregularities that later become cosmic structure. A successful early universe model has to do more than bounce. It must also produce the right statistical pattern of primordial fluctuations, one consistent with the observed universe. Some bouncing models can come close, and this is one reason they remain scientifically interesting. But matching the data while maintaining theoretical consistency is difficult. In several classes of models, the bounce itself or the growth of anisotropy can introduce problems. This does not rule bouncing cosmology out. It simply means the idea is still under construction. Still, the appeal of the bounce remains strong. It offers a universe with a history extending deeper into the past than the hot Big Bang alone. It replaces an abrupt edge with a transition. It suggests that expansion may be one half of a larger rhythm, not the entire story. And it does all this while staying within the language of physical models, rather than pure mythology. There is also a philosophical softness to the idea. A singular beginning can feel like a wall, a place where explanation stops. A bounce, by contrast, offers continuity. It does not tell us that everything appeared out of nowhere in its final form. It tells us that one cosmic phase may have grown out of another. For many people, that feels easier to imagine. The universe is still mysterious, but it is mysterious in motion rather than mystery at an abrupt edge. Of course, ease of imagination is not evidence. Nature is not obliged to be intuitive. The value of the bounce idea lies not in its emotional appeal, but in whether it can be made mathematically consistent and observationally viable. That is why physicists continue to test these models against the detailed structure of the cosmos we can measure. A bounce must not only avoid the singularity, it must also lead to a universe that looks like ours. At present, the honest verdict is that the Big Bounce remains a serious but unproven possibility. It is supported in some frameworks, especially certain quantum cosmological models, and it continues to motivate active research. It also faces real difficulties, including the control of anisotropy, the generation of acceptable primordial fluctuations, and the challenge of embedding the bounce in a fully convincing underlying theory. The idea has not failed, but it has not won. What it has done is widen the imagination of cosmology in a disciplined way. It has shown that the choice may not be only between a simple beginning and complete ignorance. There may be intermediate possibilities in which the hot birth of our observable universe was the turning point of a deeper history. If so, then the Big Bang was not a first spark in empty darkness, but the bright outward side of an earlier collapse. And that image, whether true or not, has a quiet beauty to it. The universe we inhabit may be the exhale after an earlier inward breath. A former age may have narrowed, deepened, and then yielded to release. You do not have to decide tonight whether the cosmos truly bounced. It is enough to rest with the possibility that even at its beginning, the universe may have known how to turn gently rather than break. Chapter 6. String Cosmology, Branes, and the Ekpyrotic Universe. String cosmology is one of the most imaginative attempts to look past the hot beginning of our universe, because it suggests that the Big Bang may have been not a first moment from nothing, but a transition inside a deeper cosmic setting. To understand why this idea arose, it helps to begin with the broader ambition of string theory itself. In ordinary particle physics, the basic ingredients of nature are often described as point-like particles. String theory proposes something different. It suggests that the most fundamental objects may be tiny extended entities, often pictured as strings, whose different patterns of vibration correspond to different particles. This change may sound small at first, but it can transform the structure of physics. It naturally introduces new kinds of objects, new symmetries, and in many versions, extra spatial dimensions beyond the familiar three. Among the most important of these ingredients are branes. A brane is an extended object that can have different numbers of dimensions. A point can be thought of as a zero-dimensional object, a line as a one-dimensional object, and a surface as a two-dimensional object. In the same spirit, a three-dimensional brane would be an object with three spatial dimensions. Some models inspired by string theory suggest that the visible universe could be associated with such a brane, while additional dimensions exist beyond the ones we directly experience. In that picture, ordinary matter and light may be largely confined to a brane, while gravity can probe a wider, higher-dimensional environment. This gives cosmologists a new way to think about the beginning. Instead of imagining the Big Bang as the first instant of all existence, one can imagine it as an event involving branes, fields, or extra dimensions in a larger framework. The question then changes. It is no longer simply, how did space begin? It becomes, what process in a higher dimensional or string theoretic setting gave rise to the hot expanding universe we observe? One of the earliest major attempts to answer that question was the pre-Big Bang scenario. This idea grew out of special symmetries that appear in string theory and that can relate expanding solutions to contracting ones. In this approach, the universe has a phase before the hot Big Bang in which the geometry and a string-related field evolve so that curvature and coupling grow over time. The pre-Big Bang phase is not just a replay of ordinary expansion. It is driven by the special structure of the underlying theory and is meant to describe a genuinely earlier era of cosmic evolution. The appeal of that picture is clear. It provides a past before the hot beginning, and it does so using ingredients that arise naturally in string theory rather than by adding them only for cosmology. It also offers a way to think about why the universe may have entered an extreme high curvature state. But the scenario has long faced a difficult problem. It is not enough to have a prehistory. One must also explain how that prehistory connects smoothly to the familiar hot expanding universe afterward. This issue is often called the graceful exit problem. In plain language, the challenge is to show how the theory carries the universe from the pre-Big Bang phase through the dangerous high curvature regime into the ordinary hot phase without running into inconsistencies or uncontrolled singular behavior. That difficulty is one reason another string-inspired idea gains so much attention: the Ekpyrotic universe. The word itself comes from an ancient Greek term associated with a kind of cosmic conflagration. But in modern cosmology, the idea is much more precise. In its original form, the Ekpyrotic scenario proposed that the hot Big Bang was triggered by the collision of branes in a higher dimensional setting. Our visible universe was associated with one brane. Another brane moved through the extra dimension and eventually collided with it. The energy released in that collision heated the universe and initiated the hot expanding phase we later described with standard cosmology. What made this proposal especially striking was that it did not rely on a period of ordinary inflation of the kind described in the previous chapter. Instead of invoking a burst of accelerated expansion to explain the large-scale smoothness of the universe, the Ekpyrotic picture sought to produce a smooth, flat, nearly homogeneous cosmos through a different route. In many later versions, that route involved a phase of slow contraction before the bounce or bang. During this phase, a form of energy with very unusual properties came to dominate the dynamics. It caused the universe to contract in a controlled way while suppressing some of the inhomogeneities and anisotropies that would otherwise grow during contraction. This is one of the central scientific insights of Ekpyrotic cosmology. In a generic contraction, irregularities can become a serious problem. Directional distortions tend to grow and can overwhelm the background. But an Ekpyrotic phase can, under the right conditions, damp those distortions relative to the dominant energy component. In effect, it can smooth the universe while it is shrinking. That is deeply counterintuitive because most people associate smoothing with expansion, not contraction. Yet this possibility is one reason the Ekpyrotic idea became a serious alternative in early universe research. At first, some versions of the Ekpyrotic model were described very directly in terms of brane collisions in a higher dimensional space-time. Over time, however, much of the practical analysis came to be expressed in a simpler four-dimensional effective language using scalar fields and effective potentials. That does not mean the brane picture vanished. It means that, for calculations of cosmic evolution and perturbations, researchers often worked with a lower dimensional description that captures the relevant large-scale behavior. A crucial question for any early universe scenario is whether it can explain the tiny primordial irregularities from which all later structure grew. Here, the Ekpyrotic story became more subtle than its earliest presentations suggested. The simplest single-field Ekpyrotic models do not naturally produce the observed nearly scale-invariant curvature perturbations in the most straightforward way. As a result, later work developed more refined mechanisms, especially entropic mechanisms involving more than one field, in which fluctuations orthogonal to the main background evolution are first generated and later converted into curvature perturbations. In plain language, the theory had to become more sophisticated in order to match the observed pattern of primordial structure. That refinement is scientifically important because it shows how theories evolve under pressure from data and internal consistency. The Ekpyrotic universe did not remain fixed in its earliest form. Researchers adjusted and extended it, trying to keep its core strengths while addressing its weaknesses. That process is not a sign that the idea failed. It is simply how frontier physics behaves when it is confronted with mathematical obstacles and increasingly precise observations. The Ekpyrotic scenario is also closely linked to cyclic cosmology. In a cyclic picture, the universe does not pass through only one grand transition. Instead, phases of expansion and contraction may repeat. A period of accelerated expansion can dilute matter and smooth the cosmos, after which the universe eventually enters a slow contraction, undergoes an ekpyrotic phase, and then passes through another bang-like transition. In some string or Brane-inspired versions, this repeating pattern is pictured as a regular approach and collision of branes separated along an extra dimension. Each collision creates a hot new phase, like the one we call our Big Bang. This is a remarkable shift in perspective. The Big Bang becomes not the beginning of time, but one event in a much larger history. The universe, or at least the larger structure that gives rise to our observable phase, may have no single starting point in the ordinary sense. Instead, it may renew itself through repeated transitions. Still, there are major challenges. String theory itself is not yet experimentally confirmed as a theory of nature, and the cosmological scenarios built from it inherit that uncertainty. The extra dimensions that appear in many models have not been directly observed. The detailed stabilization of those dimensions and of the many fields that arise in compactifications is technically difficult. The precise treatment of the bang or bounce transition is still one of the hardest parts of the story. In some versions, the matching through the high curvature regime remains under debate. In others, the effective description is promising but incomplete. Observationally, the situation is also mixed. Ekpyrotic and cyclic models can in principle leave distinctive signatures. For example, in the detailed statistical properties of primordial fluctuations, or in the relative weakness of long-wavelength primordial gravitational waves. But current observations have not singled them out as the unique correct explanation. Some simple versions have been constrained significantly. More elaborate versions remain viable. At present, these scenarios are best understood as serious possibilities still competing for survival, not as established descriptions of the real universe. Even so, they perform an important service in cosmology. They show that inflation is not the only logically coherent way to think about the deep past. They demonstrate that extra dimensions and branes can be used as tools for reimagining the origin of the hot universe. And they force physicists to confront one of the hardest questions of all: whether the Big Bang was truly the beginning or merely the visible face of a more hidden transition. There's a certain quiet elegance in that possibility. What we call the birth of the universe may have been the meeting point of higher dimensional structures, or the rebound from a long, smoothing contraction, or one moment in a repeated cosmic rhythm. The first light of our history may have been only the local expression of a deeper architecture we do not yet fully understand. For now, it is enough to hold the image gently. Beyond the stars, beyond the hot beginning, there may have been dimensions folded out of sight and vast branes drifting toward encounter. Or there may have been a slower, darker preparation, a universe becoming smooth before it became bright. You do not need to settle which picture is true tonight. You can simply let the possibility widen the mind, and then let it grow quiet. Chapter 7. Eternal inflation. Are Big Bangs happening everywhere? Eternal inflation is one of the most astonishing ideas in modern cosmology because it suggests that the hot beginning of our own observable universe may be only one local event inside a much larger reality that keeps producing new cosmic regions again and again. In the previous chapter, we looked at ways the universe might have had a hidden history before the hot Big Bang through string-inspired models, branes, and slow contraction. Eternal inflation offers a very different possibility. It does not mainly ask whether our universe emerged from an earlier collapse or a brane collision. Instead, it asks what happens if inflation itself, the early accelerated expansion discussed earlier, does not end everywhere at once. If inflation can stop in some places while continuing in others, then the result is a much larger cosmic picture than the one most people imagine when they hear the phrase Big Bang. The key to the idea lies in the way inflation is supposed to end. In the simplest telling, inflation is a phase during which a special form of energy causes space to expand extremely rapidly. When that phase ends, the stored energy is released into ordinary matter and radiation, creating the hot, dense conditions from which the familiar early universe evolves. In our own cosmic history, that hot beginning is what eventually leads to atomic nuclei, light, galaxies, stars, planets, and everything else we know. But in some models of inflation, this ending is not a single global event. It can happen locally in one region while other regions remain inflating. In that case, the end of inflation is not the end of the story. It is only the local beginning of one universe-like domain inside a far larger inflating background. This is why cosmologists sometimes say that the Big Bang in such a picture is really the end of inflation in our region rather than the beginning of everything. That shift in language is important. It means our cosmic beginning may be more like the birth of one habitable bubble in an immense foam of ongoing creation. The larger process keeps going. New hot expanding regions continue to form. Each one can be so enormous that it contains everything its inhabitants can ever observe, yet each one may still be only a tiny part of the whole. There are different ways inflation can become eternal. One important version is often described using the idea of a false vacuum. In physics, a vacuum does not mean absolute nothingness. It means a state of a field, often the lowest available state, or in some cases, a long-lived higher energy state that can behave as though it were temporarily stable. If space is trapped in such a metastable state with positive vacuum energy, it expands very rapidly. Quantum processes can then cause parts of that state to decay into lower energy regions. Those decayed regions behave like bubbles. Inside a bubble, inflation ends, and a hot expanding universe can begin. But the surrounding false vacuum keeps expanding, and because that inflating background grows so quickly, it can continue producing more bubbles indefinitely. In that sense, the process becomes eternal into the future. There is another route to the same general outcome. In some inflationary models, the field driving inflation does not sit in a simple false vacuum waiting to decay. Instead, it slowly rolls down an energy landscape. Even there, quantum fluctuations can matter. On average, the field may drift downward toward the end of inflation, but in some patches, quantum fluctuations can push it upward, or at least delay its descent. Since regions still inflating expand so rapidly, the total volume of inflating space can continue to grow faster than inflation ends within it. The result is again self-reproduction. Inflation stops in some places and starts local hot histories there, while elsewhere the inflating phase persists and keeps generating more opportunities for such endings. This picture can be hard to absorb because the word eternal encourages the wrong image. It does not mean that our own observable universe has personally existed forever in its present form. It means that the larger inflationary process may continue without end into the future, constantly giving rise to local post-inflationary regions. Our universe, in that view, is one of those regions. It had its own hot beginning, its own thermal history, and its own observable limits. What may be eternal is the broader background process, not our particular local cosmos. That idea naturally leads to the language of a multiverse. If many causally disconnected hot regions form within an eternally inflating background, and if conditions differ from one region to another, then the larger reality contains many distinct universe-like domains. Some versions of the idea go further and connect this with the huge landscape of possible vacuum states suggested in some approaches to high-energy theory. Different bubbles could then realize different effective laws, particle contents, or constants of nature. Whether that broader landscape picture is correct remains uncertain, but eternal inflation is one of the main physical mechanisms by which such a multiverse is often imagined. For some cosmologists, this is an exciting explanatory possibility. Certain properties of our universe might then be understood partly as environmental. We would observe them because only some types of cosmic regions allow galaxies, chemistry, long-lived stars, and observers. For others, this move is deeply uncomfortable because it seems to blur the line between explanation and selection. If almost every possibility exists somewhere, then prediction becomes much harder. Instead of asking what the theory uniquely demands, one must ask how to assign probabilities across an enormous collection of different regions. That problem is one of the central difficulties of eternal inflation. It is usually called the measure problem. The trouble begins because eternal inflation often produces not merely many regions, but effectively infinitely many. If every allowed type of bubble occurs endlessly many times, how should one compare their frequencies? Different ways of slicing the space-time, or counting the bubbles, or restricting attention to particular observers can lead to very different answers. A prediction then seems to depend not only on the underlying theory, but on the procedure used to count outcomes. This is not a minor technical nuisance. It touches the heart of whether eternal inflation can make clear probabilistic predictions at all. Even setting that aside, one can still ask what a bubble universe is like from the inside. If our observable universe formed within such a bubble, then to us it would not necessarily look exotic in any immediate way. After inflation ended locally, reheating would fill the region with hot radiation and particles, and ordinary cosmological evolution would proceed. The local universe could become extremely large and nearly homogeneous. To observers living inside, everything might look much like standard cosmology, at least across the portion they could see. The larger inflating background would lie beyond any direct view. In principle, however, there might be clues. If bubbles form and expand within a larger inflating space-time, some of them can collide. A collision between bubble universes could leave traces in the observable sky of a region like ours, perhaps as large-scale asymmetries or unusual patterns in the oldest light. This possibility has motivated serious attempts to search for observational signatures of bubble collisions. So far, no widely accepted detection has emerged. That does not mean eternal inflation is false, but it does mean that its most dramatic predictions have not yet found decisive support. There is another important limit to keep in mind. Eternal inflation into the future does not automatically tell us that the whole cosmos is eternal into the past. In fact, an influential result in cosmology shows that under broad assumptions, space-times that are on average expanding cannot be extended indefinitely backward along every geodesic. In plainer language, even if inflation keeps generating new universes forever into the future, that by itself does not remove the need for some deeper account of the past boundary. Eternal inflation may radically change what the Big Bang means, but it may not eliminate the question of a beginning altogether. That point gives eternal inflation an unusual place in this video. On one hand, it strongly weakens the old picture of the Big Bang as the unique beginning of all existence. Our own hot beginning may have been only one regional event among many. On the other hand, eternal inflation may not answer the deepest question of why there is an inflating background at all, or what set its earliest conditions, or whether it must ultimately arise from some quantum beginning, bounce, or other more fundamental framework. So the theory is both expansive and incomplete. It opens the door to cosmos unimaginably larger than the observable universe, possibly populated by endlessly many bubble regions, perhaps with varied properties. Yet it leaves major conceptual burdens behind. The measure problem remains unresolved. Direct observational confirmation remains absent. The status of the larger multiverse picture depends heavily on details that are still speculative. And the ultimate past of the inflating space-time may still require new physics. Still, there is a reason this idea has had such a lasting hold on scientific imagination. It takes the success of inflation seriously and follows the mathematics where it may lead, even when the destination becomes unsettling. If inflation really can become self-reproducing, then the cosmos may be less like a single expanding universe and more like a vast engine of continual beginnings. Big bangs would not be rare exceptions. They would be local outcomes of an ongoing process happening somewhere almost all the time. That image can feel overwhelming at first, but it can also feel strangely peaceful. Our universe would still matter. Our stars would still shine. Our history would still be real. it would simply be one bright chamber in a structure far larger than we can ever see. If that is true, then the night sky is not the whole stage, but only the small visible interior of one bubble among many. And as that thought settles, it need not feel lonely. It can feel quiet, spacious, and oddly gentle, like realizing that reality may be wider than even wonder first imagined. Chapter 8. A Universe Before Ours. Penrose's Conformal Cyclic Cosmology. Conformal cyclic cosmology is one of the most unusual ideas in all of modern cosmology, because it suggests that the unimaginably remote future of a previous universe could, after a deep mathematical reshaping, become the beginning of our own. At first, that sounds almost impossible. In ordinary thinking, the end of a universe and the beginning of a universe seem like opposite things. One sounds like fading away, the other like explosive birth. But Roger Penrose's proposal asks us to think less in terms of ordinary appearance and more in terms of the geometry that remains when size itself stops mattering. The key word is conformal. In geometry, a conformal transformation preserves angles and causal structure, but it can stretch or shrink lengths by an overall factor. If the detailed notion of size becomes physically irrelevant in certain extreme regimes, then two very different-looking states of the universe can turn out to share the same conformal structure. That is the doorway into the theory. Penrose proposes that the universe does not exist as a single one-time expansion followed by a final end. Instead, it consists of successive cosmic eras, which he calls aeons. Each aeon begins with something like a Big Bang and expands for an immense span of time. Eventually, if the universe continues to expand under the influence of dark energy, matter becomes ever more dilute, stars die, black holes evaporate, and the cosmos approaches a thin, cold, empty future. Penrose's claim is that this remote future can be joined conformally to the Big Bang of the next aeon. In that sense, what looks like the end of one universe becomes the start of another. To see why he thinks this is possible, we need to ask what the universe would be like in the far future. In ordinary experience, size is meaningful because we compare one object to another. But Penrose argues that in a universe emptied of bound structures, with matter no longer playing its usual role, scale can lose physical significance. If the late universe becomes dominated by massless radiation and other scale-free phenomena, then the distinction between extremely large and extremely small can fade in importance. A conformal rescaling can then compress the vast remote future of one eon into something mathematically equivalent to the hot beginning of the next. This does not mean that a gigantic old universe literally shrinks down inside a pre-existing container. It means that the equations can be reformulated so that overall scale is not the fundamental issue. What matters is the pattern of light-like directions, the causal relationships, and the conformal geometry. In Penrose's picture, once all massive particles either disappear or effectively cease to set a preferred scale, the infinitely expanded future can be reinterpreted as a finite boundary. That boundary is then identified with the initial surface of a new aeon. This is one of the most radical features of the idea. In many cyclic models, one imagines an expansion followed by a contraction and then a bounce. Conformal cyclic cosmology is different. It does not require the universe to reverse and collapse. The expansion can continue forever. The bridge from one eon to the next comes not from a literal turnaround in size, but from a change in how size is understood. The future becomes so empty and scale-free that it can be conformally matched to a new beginning. There is also a strong thermodynamic motivation in the background. One of Penrose's long-standing concerns has been the extraordinary low entropy of the early universe, especially its low gravitational entropy. The early cosmos was hot and dense, but it was also remarkably smooth. That smoothness is not a high entropy state for gravity. Left to itself, gravity tends to produce clumping, collapse, and black holes. A universe full of black holes carries enormous gravitational entropy. So the puzzle is not why the early universe was hot. The puzzle is why it was gravitationally so ordered. Penrose's broader answer involves what he calls the Weyl curvature hypothesis. In simplified terms, he suggests that the gravitational field near the beginning of an aeon is constrained so that certain curvature degrees of freedom associated with gravitational disorder are absent or extremely suppressed. This helps encode the low gravitational entropy of the initial state. Conformal cyclic cosmology then tries to explain why such a special beginning could arise again and again. If the remote future of one aeon sheds almost all the sources of gravitational complexity, especially after black holes have evaporated away, then the transition to a new low-Weyl beginning may become possible. Black holes therefore play a central role in the story. In Penrose's picture, much of the gravitational entropy accumulated during an aeon is eventually locked into black holes. Over extremely long periods, those black holes evaporate through Hawking radiation. As that process continues, the universe is stripped of its most extreme gravitational structures. What remains in the idealized future is a universe in which the dominant content is effectively massless and diffuse. This is the sort of state Penrose believes can pass conformally into a new aeon. At this point, an obvious question appears. Do massive particles really go away? In the world we know, particles with rest mass help define scales. Their existence seems to resist the claim that size becomes irrelevant. Penrose has argued that, in the very remote future, the physics should be describable in a way where mass either disappears in significance or is not fundamental to the crossover. This is one of the more debated aspects of the proposal. Many physicists regard it as a bold assumption rather than an established consequence of known physics. It is one of the reasons conformal cyclic cosmology remains intriguing but controversial. Another important issue concerns the actual crossover between aeons. It is one thing to state that the end of one aeon and the beginning of the next are conformally related. It is another to specify the exact equations that govern that matching and to show that the procedure is unique and physically well-defined. Considerable mathematical work has gone into formulating this crossover more precisely, but it remains one of the technical challenges of the theory. Even so, the theory makes a distinctive conceptual move. It treats the Big Bang not as the first moment of all reality, but as the conformal continuation of something earlier. Our universe would then have inherited a deep past, not by direct memory in the ordinary sense, but through the geometry of a previous aeon. The cosmos before ours would have had its own stars, galaxies, black holes, and history. It would have aged almost beyond imagination, gradually emptied out, and only then, after conformal reshaping, given way to our beginning. That naturally raises the possibility of observational traces. Penrose and collaborators have argued that violent events late in a previous aeon, especially encounters involving supermassive black holes, might leave subtle imprints in the cosmic microwave background of our own aeon. Claims have been made about concentric low-variance circles and later about small hotspots, sometimes called Hawking points. These claims attracted substantial attention because they seem to offer a way to test a theory that otherwise sounds almost metaphysical. But the observational status of these claims remains unsettled. Other researchers have argued that the reported features are not statistically compelling once the data are analyzed in different ways or compared properly with standard cosmological expectations. In the broader scientific community, these alleged signals have not been accepted as decisive evidence for conformal cyclic cosmology. That does not prove the theory wrong, but it means that the strongest publicized empirical support for it remains disputed. This pattern is common in frontier cosmology. A theory can be mathematically imaginative and physically motivated without yet being established by data. Conformal cyclic cosmology is exactly such a case. It offers a genuine framework, not just poetic language. It is grounded in conformal geometry, thermodynamic reasoning, and the expected long-term behavior of an expanding universe with dark energy. It also depends on assumptions that are not part of standard confirmed physics, especially regarding the effective loss of mass scales and the precise treatment of crossover between aeons. Whether nature truly works this way is still unknown. Many cosmologists remain skeptical. Some think the assumptions are too strong. Others think the observational claims are too weak. Others simply prefer models more directly connected to inflation or quantum gravity. Yet even its critics often recognize that conformal cyclic cosmology asks an unusually deep question. What if the far future and the deep past are not opposites, but secretly the same kind of boundary viewed through different scales? That is the quiet power of the idea. It invites us to imagine that the universe inherited its dawn from another cosmos that had already spent itself completely. Our Big Bang would then be neither an isolated miracle nor a simple restart. It would be the next aeon's sunrise after a night so long that size itself had faded from meaning. And perhaps that is a gentle image to end with. Before our stars, there may have been other stars. Before our galaxies, other galaxies. Before our beginning, another universe growing old in the dark until even vastness became weightless and thin. You do not need to decide tonight whether that vision is true. It is enough to let it widen the silence a little, and to rest inside the thought that even endings may sometimes be another form of beginning. Chapter 9. Could anything from before the Big Bang still be visible today? For all the strange ideas about what may have come before the Big Bang, the most important scientific question is not simply whether those ideas are imaginative, but whether any earlier cosmic phase could have left fingerprints that still survive in the universe around us today. This chapter is where cosmology becomes disciplined. It is one thing to propose a bounce, a quantum beginning, an eternal inflating background, or a previous aeon. Science does not advance by offering many stories and choosing the most beautiful one. It advances by asking what the universe would look like if one story were true rather than another. So the question before us is very precise. If something happened before the hot Big Bang, what traces could it leave behind, and where would we look for them? The first part of the answer is humbling. We cannot look directly past the hot early universe using ordinary light. The oldest light we can observe is the cosmic microwave background, released when the universe had cooled enough for light to travel freely through space. Before that time, the universe was opaque. Light was constantly scattered and could not carry us farther back in a simple, direct way. So when people imagine a telescope looking straight through the Big Bang into an earlier cosmos, that is not how observation works. If there was a prehistory, we do not see it directly with photons. We look instead for indirect consequences that an earlier phase may have imprinted on the conditions from which the visible universe emerged. That point is crucial because it tells us what counts as evidence. A pre-Big Bang phase, if it existed, would matter today only if it influenced the initial pattern of the hot universe. It would have to leave some mark on the distribution of matter, the pattern of the oldest light, the background of gravitational waves, or the statistical properties of cosmic structure. In other words, the earlier phase would need to hand something forward across the transition. If no information survives, then the idea might remain mathematically possible, but observationally unreachable. The cosmic microwave background is therefore one of the most valuable places to look. It is not a photograph of the ultimate beginning, but it is an exquisitely detailed snapshot of the young universe. Across the sky, it contains tiny temperature differences and subtle polarization patterns. Those small variations reflect primordial irregularities that were already present long before atoms formed. They are the seeds from which all later cosmic structure grew. Because these irregularities were laid down so early, they act like a fossil record of deep cosmic history. This is why so many theories about what came before the Big Bang are judged by the primordial fluctuations they predict. Different early universe scenarios generate different patterns. Some produce perturbations that are almost, but not exactly, the same on different length scales. Some produce a characteristic amount of primordial gravitational waves. Some predict special correlations between fluctuations at different points in the sky. Some allow oscillatory features, cutoffs, or asymmetries on the very largest scales. The observations do not merely ask whether the universe is smooth or lumpy. They ask about the exact statistical texture of those lumps. One of the most discussed targets is primordial gravitational waves. These are ripples in space-time generated in the early universe itself. Unlike light, gravitational waves interact extremely weakly with matter, which makes them hard to detect, but also makes them extraordinary messengers from very early times. If a process before or during the transition to the hot Big Bang generated a background of primordial gravitational waves, part of that signal could in principle still be present today. It might be sought through delicate patterns in the polarization of the cosmic microwave background, or through direct searches for a stochastic background at much later frequencies. This is one reason gravitational waves are so exciting in this subject. They can, in principle, probe eras earlier than those accessible by ordinary light. Inflation can produce a primordial gravitational wave background. Some bouncing and pre-Big Bang scenarios can also produce distinctive gravitational wave spectra, sometimes with a different dependence on frequency or power than standard slow-roll inflation would suggest. In that sense, gravitational waves are one of the few channels through which genuinely pre-hot Big Bang physics could announce itself. But even here, caution is needed. A gravitational wave detection would not automatically tell us that we had seen before the Big Bang. Many different early universe mechanisms can produce gravitational waves. Astrophysical sources can also contribute backgrounds of their own. The scientific task is therefore not only to detect a signal, but to infer its shape, origin, and compatibility with competing models. Another important clue lies in what cosmologists call non-Gaussianity. The word sounds technical, but the idea is simple. If the primordial fluctuations were generated in the most minimal and orderly way, their statistics should be very close to a Gaussian random field, meaning their overall pattern would be described largely by their variance and power spectrum. More complicated early universe physics can create additional patterns, subtle higher-order correlations that go beyond this simplest random structure. These patterns can encode information about the fields, interactions, or transitions that shaped the very early cosmos. This makes non-Gaussianity a powerful tool. It can help distinguish between different versions of inflation, between inflation and some alternatives, and between simple and more complicated dynamics near the beginning. Some bounce models, multi-field scenarios, and other non-standard histories can leave stronger or differently shaped non-Gaussian signatures than the simplest inflationary models. Observations so far have placed strong limits on large primordial non-Gaussianity, which means many exotic constructions are more constrained than they once were. Large-scale anomalies in the sky are another place people often look. Over the years, cosmologists have noticed certain unusual features in the largest angle patterns of the cosmic microwave background, such as hints of hemispherical asymmetry, low large-scale power, or other departures from perfect statistical simplicity. It is tempting to connect such anomalies to exotic physics before the hot Big Bang, perhaps a bounce, a previous aeon, unusual topology, or even a collision with another bubble universe. These ideas are scientifically worth exploring, but the evidence must be treated carefully. Bubble collision searches provide a good example of this caution. In eternal inflation, if our observable region formed inside a bubble and another bubble collided with ours in the deep past, the collision might leave a broad circular or disk-like imprint in the cosmic microwave background. This possibility has motivated real data analyses, and it is a beautiful example of how even a seemingly extravagant multiverse idea can be turned into an observational question. So far, however, no candidate signal has been accepted as compelling evidence. The absence of a confirmed detection does not eliminate eternal inflation, but it shows how hard it is to move from speculative possibility to persuasive proof. The same is true for conformal cyclic cosmology. Penrose and collaborators have argued that a previous aeon might leave unusual structures in the microwave background. Those claims drew attention because they offered a concrete route by which a universe before ours might still be visible. Yet the statistical case remains disputed, and most cosmologists do not regard the proposed signals as established. There are also possible relics besides patterns in ancient light. Some theories suggest that very early transitions could produce topological defects, such as cosmic strings or relic particle populations, or distinctive small-scale structure, or backgrounds of gravitational waves at frequencies far removed from the microwave sky. In principle, any of these could carry information from very early epochs, but they are usually not unique signatures of a pre-Big Bang phase. Perhaps the deepest lesson is that evidence from before the Big Bang would most likely not look like a message saying there was a universe before this one. It would appear as a mismatch between observation and the simplest standard expectations. It might be an unexpected tilt or cutoff in the primordial spectrum, a special pattern of polarization, a gravitational wave background with the wrong shape for minimal inflation, a consistent non-Gaussian signal, or a statistically robust large-scale feature that ordinary models struggle to explain. The earlier universe, if it left traces, would speak through structure, not through narration. This is why current cosmology is both exciting and restrained. Measurements of the cosmic microwave background have reached astonishing precision. Large-scale galaxy surveys now map structure across enormous cosmic volumes. Gravitational wave astronomy is opening a new observational channel. Future experiments may measure primordial polarization more sensitively, probe stochastic gravitational wave backgrounds more deeply, and test the statistics of primordial fluctuations with greater power than ever before. For the first time in history, questions that once sounded purely philosophical are being translated into concrete observational programs. And yet the answer, at least for now, remains careful. Could anything from before the Big Bang still be visible today? Yes, in principle. An earlier phase could have left fossils in primordial fluctuations, polarization, gravitational waves, or other relic signatures. But no observation has yet provided universally accepted proof of a specific pre-Big Bang scenario. We have hints, frameworks, and increasingly refined tests. We do not yet have a settled detection of a previous universe. That may sound disappointing, but it is actually a sign of scientific maturity. Cosmology has moved beyond simply wondering what came before. It is now asking where such a past would hide in the sky, what exact marks it would leave, and how to tell those marks from noise, coincidence, or ordinary early universe physics. The mystery is no longer vague, it has become measurable. So perhaps the most honest ending to this chapter is also the calmest one. If there was something before the Big Bang, it may not be gone completely. A faint memory of it could still be drifting through the oldest light, trembling through space-time, or woven into the first irregularities from which all later structure grew. We do not yet know if that memory is really there, but we know where to listen. And for tonight, that is enough. The universe has not fallen silent. It may still be whispering about what came before, very softly across the dark. Chapter 10. What science can truly say about before the beginning. After all the ideas we have explored, from inflation to quantum beginnings, from bounces to branes, from eternal inflation to conformal cycles, the most important question is no longer which picture feels most dramatic. The real question is much quieter and more difficult. What exactly is science justified in saying when it speaks about what may have come before the beginning of our observable universe? The first honest answer is that science does not yet possess a complete theory of the beginning. Modern cosmology is extraordinarily successful at describing the universe once it is already in a very hot, dense, expanding state. It explains the relic glow of the early universe, the broad abundance of the lightest elements, and the growth of cosmic structure from tiny primordial irregularities. But when the known equations are pushed back toward the deepest origin, they reach a regime where classical gravity is no longer enough. At that frontier, the standard description becomes incomplete rather than final. That matters because it tells us why the question remains open. If our best established framework already gave a complete and tested account of the first physical moment, then speculation about an earlier phase would be little more than imaginative decoration. But that is not the actual situation. The known theory works brilliantly for much of cosmic history, then approaches a boundary where quantum effects and gravity must somehow be joined. The space beyond that boundary is not a blank invitation to fantasy. It is a real scientific problem created by the success and the limit of the theories we already have. The second honest answer is that the word before may or may not be physically meaningful, depending on the deeper theory. In everyday life, before is simple. It means earlier in time. But if time itself is part of the structure that emerged with the early universe, then the question may need to be reformulated. Some proposals treat the beginning as the emergence of classical time from a quantum regime. Others replace a singular start with a transition from an earlier phase. Still others suggest that our hot beginning is only a local event inside a much larger cosmic process. So science cannot yet say in one universal sentence what before means. It can only say that the answer depends on which underlying description of reality is correct. That brings us to the range of serious possibilities. One class of ideas says that the hot Big Bang was preceded by inflation, a rapid early expansion that prepared the conditions of the later hot universe. In that picture, the Big Bang of ordinary cosmological history is not the absolute first moment, but the aftermath of an earlier phase. Another class says that the universe may have emerged through a quantum process, so that the beginning was not a classical event at all. Another suggests that expansion was preceded by contraction, and that the apparent beginning was really a bounce. Still others explore higher dimensional settings, repeated cycles, or self-reproducing inflating regions in which many hot beginnings occur. These are not identical ideas, and they do not carry equal support, but they show that modern cosmology contains several mathematically serious ways of going beyond a simple singular starting point. At the same time, science must be careful not to confuse live research programs with established facts. Inflation is broadly compatible with observation and explains several important features of the universe well, but the detailed mechanism behind it is still uncertain. Quantum beginning proposals are conceptually rich, yet they rely on a quantum theory of gravity that is not complete and experimentally confirmed. Bounce models are attractive because they try to avoid a singular edge, but they face substantial theoretical challenges. String-inspired and Ekpyrotic scenarios open impressive possibilities, but they depend on wider frameworks that remain unverified. Eternal inflation follows naturally from some inflationary models, yet it introduces deep conceptual problems about prediction and probability. Conformal cyclic cosmology is imaginative and mathematically distinctive, but it remains controversial. In other words, none of these possibilities has yet earned the status of settled truth. This leads to the third honest answer. Science can compare hypotheses, but it has not yet chosen a winner. That may sound frustrating, but it is actually a sign of intellectual discipline. A mature science does not pretend certainty where certainty has not been earned. It weighs explanatory power, mathematical consistency, and observational consequences. It rules out weak versions of ideas, refines stronger ones, and keeps asking better questions. The current state of cosmology is not confusion in the simple sense. It is a field in which several deep possibilities remain open because the decisive evidence has not yet arrived. That evidence, if it comes, will not look like a label in the sky saying there was a universe before ours. It will come in the form of patterns. It may appear in the statistics of primordial fluctuations, in delicate polarization signals in the oldest light, in a background of gravitational waves, or in some robust large-scale feature that the simplest picture fails to explain. Theories about what came before the Big Bang matter scientifically only when they risk contact with observation. This is why the most serious versions of these ideas are not merely stories about hidden worlds. They are attempts to describe earlier phases in ways that could, at least in principle, leave observable traces in the universe we can measure. There is also an important limit that science itself reveals. Some theories can weaken the idea that our Big Bang was the beginning of everything, but that does not mean they eliminate the question of origin completely. Even inflationary models that keep producing new cosmic regions into the future do not automatically explain their own past boundary. Some cyclic ideas push history further back, but still require a detailed and consistent transition law. Quantum origin proposals may replace a classical beginning with a deeper framework, but then one may still ask why that framework exists and has the form it does. Science can move the question, sharpen the question, and sometimes dissolve part of the question. It does not guarantee that every human form of why will receive a final physical answer. That is why it is useful to separate different kinds of mystery. One mystery is physical. What equations and states best describe the earliest accessible regime, and what observational signatures follow from them? Science can work on that mystery directly. Another mystery is philosophical. Why there is a lawful reality at all, why those laws exist rather than others, and why mathematics connects so deeply with nature. Physics may illuminate these questions, but it may not close them in the same way it closes questions about planetary motion or stellar evolution. Recognizing that distinction does not weaken science. It protects its strength by keeping its claims honest. So what can science truly say at this point? It can say that the hot Big Bang was not an explosion into empty space, but the early hot expansion of our universe. It can say that the standard cosmological model does not by itself provide a final account of the deepest beginning. It can say that several serious frameworks suggest the hot Big Bang may have been preceded by something else, whether a rapid inflationary stage, a quantum origin, a contracting phase, a higher dimensional process, a self-reproducing inflating background, or a previous aeon. It can say that these ideas are constrained by observation and by mathematical consistency, and that none has yet been confirmed as the uniquely correct description. It can say that cosmology has turned what once sounded like pure metaphysics into a set of testable, if extremely difficult, scientific questions. And perhaps that is already remarkable enough. Human beings living on one small planet around one ordinary star have reached the point where the question of what came before the beginning is no longer only a poem or a myth. It is a frontier problem in theoretical and observational science. The answer is not finished. The deepest chapter of cosmic history is still partly unread. But the fact that we can even frame the question with this much precision is one of the quiet triumphs of thought. So the final scientific lesson is not that we now know what came before the Big Bang. We do not. The lesson is something gentler and, in its own way, more beautiful. Science has shown us exactly where knowledge becomes uncertain, exactly why the uncertainty appears, and exactly which kinds of ideas might carry us further. It has transformed a vague wonder into a disciplined search. And that may be the right place to leave the journey tonight. You do not need the universe to surrender its first secret before you can rest. It is enough to know that the question remains open for good reasons, and that the silence around the beginning is not empty. It is full of careful thought, patient observation, and possibilities still unfolding. Let that be calming. Let the question stay larger than you for a little while longer, and let the mind, having followed it all the way to the edge, grow quiet there. And now, my friend, we have reached the edge of this journey. If you are still awake, you can stay with the channel and choose another video to keep you company through the night. But if sleep is finally beginning to find you, then let the questions grow quiet. Let the stars fade softly into the background and let your mind rest. Sweet dreams among the stars, my friend.